It's the, yeah. Make sure you can see it. Just kidding. Well, you know, if it's AC, you know that right through the center is 0. It means if it's AC, it has to be going positive and negative.
Right.
And the only time, the diode is sensitive to that polarity, isn't it? You do know that, right?
What I can't figure out is what part is hitting the anode and what part is hitting, and why it's hitting the anode and why it's hitting the cathode.
In what direction? See, if it hits the cathode first, then it's on.
Yeah, no, if,
Well,
well,
that's where I'm getting confused.
what you have to do, because it's a sine wave over time, you have to look at it when it's positive, this time and this time. The rest of the points, this point, this point, and this point, it's at 0, so nothing's gonna happen there, right?
Right.
So, when this is 0, you're gonna get 0, 0 there, and 0 here. When this is maximum positive, which would say, we can say it's, we'll use 10 volts or something, right? When that's positive, is the diode on or off? That's at this time right here. Now you understand, at that point right there, it's at 10 volts. How's the diode gonna respond to that? Since it's a plus 10, and the anode, the plus 10 is connected to the anode, you can say the diode is on. And when it's on, you know it's a direct short. It's a switch. Remember, diode's an electronic switch. Right? You okay with that?
I'm okay with that part of it.
All right.
I just,
So when it's on, that's a direct short, and that voltage right there is going to appear on the output, isn't it? And then all you do is connect the dots. Now we look at when it's maximum negative, at this point right here. Now the signal's sitting there at maximum negative. Can you see that the anode is going to be negative with respect to the cathode?
that's when it turns off.
When it turns off, it's like an open switch. Mechanically, it looks like this. Right? It's open. So what are you going to get across the load? 0. So you do that, connect the dots, done. That explains why with one diode you can generate a half-wave rectifier.
So,
In other words, you're eliminating the negative half of the wave. So go ahead.
so if you turn the diode around, it would do the same thing, just on the negative cycle, right?
Yes, if you turn the diode around, what would happen during the positive, if this is actually the cathode now, when it's positive, the cathode or the anode is going to be negative with respect, it's going to be off, so you get a 0. Then when this goes negative,
It's on.
that now the anode's positive is going to be on, and so that negative would appear there, and so it would look like that.
But you would get a continuous, it would only be on when it was negative.
Yeah, it would be a continuous, instead of being positive like this, continuous, it's going to be negative. During the positive time, it'd be negative, and when it was negative, you get the picture? 0 minus, and this is 0 plus. So you can get any polarity out of the out of that circuit. You can get either positive or negative, but that's all that circuit can do. It's a half-wave rectifier, and it has very little application, but it does have some application. And the application is for charging a battery. It's a cheap way to charge a battery. Because all you need, let's say you have a 12-volt battery. And remember we did this last week? If this is, let's say this is a peak, let's say this is, let's make it a 24-volt peak. And so this is negative 24. So the peak-to-peak voltage is 48. All right. Now, we apply this 24 volts to this circuit right here, as it's shown, if we apply that 24 volt peak, what's gonna happen out here on the output well is gonna go to 24, because all of it, that's a direct short. Remember, first approximation, it's a direct short. All that 24 volts peak is gonna be there, and then, of course, when it goes negative, during this time, it shuts off, and it's gonna be 0, so we have our DC. What kind of DC is it? Anybody?
Pulsating.
Pulsating. Why is it pulsating? Because it touches 0 but doesn't cross. That's what we call pulsating. All right, now, what's a voltmeter gonna read?
24 volts.
Jeff, I'll give you 5 points extra credit if you'll give me that answer, and nobody else say what. What's a voltmeter gonna read? We talked about it last week.
When it's what, very short?
When the wave that's generated is this half-wave rectified output, which has a peak of 24 volts. What's the voltmeter gonna read? Remember, it's DC, and what do DC meters read? Peak, peak to peak, RMS, average, or they don't read at all? Guess that's an option.
I got a 50-50 shot. This is 0 volts, I don't know, 24 volts. 0 volts.
Got your notes?
Not my full known.
Hey guys, flip your notes back to last week.
We didn't put it in RMS. It's already in.
Since it's DC, this 24 peak to peak, or 24 peak, we don't care about RMS right now, but, what's that say there, Jeff? DC, all DC meters read what?
Be the, average,
They read the average, right?
yeah, 6.636.
Well, you can use that, or you can use, average is, it's 63.7%. And if you want to do that, that's fine. But we know, I told you the equation I want you to remember is RMS equals 0.707 times the peak. And average is what? What I gave you last week?
90% of RMS.
Okay, so if we want to get I just said get the RMS first. Take 0.707 times 24. That's all you gotta do. What's 70% of 24?
16.96.
So 17 volts. Can we say that?
Yeah.
So the RMS is 17 volts. Remember, if it's not labeled, it's assumed to be what? RMS. Why? Because all 18 meters read RMS. That's what they read, the RMS. So if the RMS is 17, what's the average?
About
90% of that.
15.
Or you take 10%, that'd be 17 minus 1.7.
Yeah, so 15.27 or 0.3.
Call it 15.3.
Yeah.
Okay, so the average is 15.3. So, Jeff, what's the voltmeter gonna read for that circuit out here across that load? 15.3. The other thing you wrote in your notes last week, at least if you did what I told you, it would say that the average, when you read average, it reads the average for one complete cycle. And the average for during this time is 15.3. But since it's 0 half the time, we have to divide that by 2. Which is 17.65 or something?
Yeah, 635.
Yeah. About, what'd you say it is?
7.6.
Yeah. So the,
64.
what you're gonna get out of here is about 7.6 volts, isn't it? Now, we started out with an RMS of 17, and all we get out of this DC, AC to DC converter is 7.6. That's not very efficient. Is it? It's pretty bad. But if you have a 6-volt battery, that would charge a 6-volt battery, wouldn't it? Remember, 12 volts on a typical car, GM, is about 14.6 charging volt regulated output to charge the battery. 14.6. Well, if it's 6 volts, it'd be about half of that. 7.3 or 7.6 was perfect, would be perfect for charging a 6-volt battery. And you say, well, what if it overcharges? I mean, you can, all you're saying is all you got needs is a transformer, one diode, and you got a battery charger? Absolutely. In fact, I could build that and put a case around and say automatic. That's all you need, and then you can charge $19.95 for it. It's automatic. That means that the current will adjust according to the charge on the battery. Wow, well, that's pretty cool. And it will, and this one will, because a dead battery is like a short. A dead battery is going to be about 10 ohms resistance. But as it charges up from 0, as it charges up, the resistance goes up. Instead of being low resistance, it goes to high resistance. And so it automatically limits the current, you see. Like its resistance automatically changes. And so it works great. I used it for years on my little 1992 diesel Chevy truck. I park it outside my lab, which I'm there from 7:30 to 4 every day. And I built that little charger, and I put it on cold days. I just run the wire through the door, set the little charger on the hood of the truck, and put on the battery. And when I get in there at the end of the day, the battery's nice and warm, and start right up. Now back then, diesel trucks, either had to have heaters or really good glow plugs or something. But anyway, I just did it for novelty, just to show them that it starts out kind of like drawing lots of current because it's low resistance, but as the battery charges up, it goes towards an open. As long as you know that this makes a good battery charger. This is your battery out here, plus and minus. That's simple.
If you overcharge the battery, doesn't it take away some of its life though?
Sure. How are you gonna overcharge it though? I mean, if you use a 2-amp transformer here, you have to limit the current to 2 amps, you know, or whatever. Anytime you're charging a car battery at 1 amp or so, you would have heard it. I mean, you can charge it 1 amp for a month. In fact, I've had batteries out of my tractors. If I'm not driving the tractor all winter, I take the battery out, put it in my basement, and I put it on a trickle charge for the entire winter.
So as long as you're not overloading with current, it'll be fine?
Right. When you overload, you gotta be putting a lot of current into them. You gotta remember, these are like 700 and 800 amp hour batteries. That means that they can deliver up 800 amps for an hour before they're dead. How long would it take to put 800 amps back into a discharged battery at 1 amp a long time?
My wife got a house actually has
Well, roughly
6 amp.
at 1 amp, it'd take at least 700 hours. And
6 amps wouldn't take, 6 amps wouldn't take long at all.
to charge a battery.
A 12 volt.
Yeah, 6 amps is pretty good. You know, you can charge them up in an hour or two. But it's pretty hard. You can't overcharge a car battery with a limit of 3 to 5 amps, or even probably 10 amps, because they're not going to draw any current when they're full. As they get more and more charged, they get higher and higher resistance. The current gets down to almost nothing because the resistance, the current's dependent on the load, right? So this load goes, it's like a potentiometer. It's going from 10 ohms to about 150 ohms. So if it's drawing 10 amps discharge, it'll draw 1 amp charge. That's why when the needle gets all the way over and it says green, you know it's fully charged. Okay, well, I'm just trying to give you I just want you to be able to determine the output voltage of a halfway rectifier, understanding its average, and measure the average for one complete cycle. And therefore, if you get the average of this cycle here, and it's 0 the next 50% of the time, you gotta divide by 2. That's just the way it is when you have average. You're the average of anything. If you're going 60 miles an hour, and then all of a sudden you stop, and then the clock's still running, what's the average? Well, it's gonna be 30, if you don't go any further. Any questions on that? And if you want to remember 63.7%, that's okay to do that. I'm just saying, I would always start there. Everything's measured in reference to the RMS, because that's the true power of an AC wave, isn't it? So if you know the RMS is always 0.707 times the peak, and you know the average is 90% of that, all you gotta do is move the decimal and add it to it, and you're done. Actually, subtract it from it. Yeah. Any questions? We need to roll on here? Well, that was one of the, kind of like one of the circuits you had to explain, isn't it?
Number 2.
You ought to get that one done today. We got 3 more to go. You got a 3-page paragraph, buddy.
Yeah.
All right? I'm gonna go ahead and explain talk about the transformer, that guy right there. You guys had 111. What do you know about a transformer? Give me something, what do you need to know to determine what the voltage is going to be out of a transformer? What do you need to know? What? Turns ratio. Everybody know what he means by turns ratio? Turns ratio is always the primary winding with respect to the secondary winding. The primary is where you put the AC power, the 120 volts, based on house wiring circuitry. Remember, if I say 120 volts and it's not labeled, what voltage is it? Everybody said what?
RMS.
RMS. So if the RMS is 120, and I have a ratio of, we'll say, well, just keep it simple as possible, 2 to 1. What that says is for every 2 turns on the primary, there's going to be 1 turn on the secondary, if the ratio is 2 to 1. That's what that means, right? It's the turns ratio, the number of turns on that primary with respect to the number of turns on the secondary. So the voltage from here all the way to here, assuming that there's nothing connected to the CT, which stands for center tap. If there's nothing connected there, the voltage from there to there would be 60 volts. That's the RMS voltage, so it's not labeled. Questions? And if I came across here, and from here down to here, and I put a resistor out here, this voltage here has an RMS of 60 volts, and it has an average, assuming I put a diode here, one diode right there. See, once you get on this side of the diode now, it's no longer AC, because the diode only operates in one direction. So since this is a DC voltage, what's going to be that voltage across the load? Well, the waves across this load resistor RL this wave out here is going to look like this. Right, with respect to the AC wave coming in. Zero. I know this has an RMS, this wave has an RMS of 60. Since this is DC, I want the average, and this average would be 54. 90% of 50. Or 90% of 60. 6 times 9 is 54, you know, 90%. All right, so what's the voltmeter going to read?
27.
Say it again real loud.
27.
27. Did you say that, Jeff?
Sure.
Did I hear you?
Yeah, I was in there.
Great, we're there. It is 27. And why do you think it is, Jeff?
It'd be divided by 2.
Because it's the average for one complete cycle, and it's 0 half the time, so we got to divide it by 2. Now notice, we put in 60 cycles, or 60 volts. True power is 60 volts to that AC wave, and we're getting out 27 volts DC. Would you say DC is more or less efficient than AC?
That's still gonna charge.
It's not even 50% as efficient as AC.
Yeah, but it'll charge your 12-volt battery.
Huh?
It'll charge your battery.
Yeah, I don't know if I want 27 volts charging a 12 volt, but.
Bigger battery.
Yeah, a 24 volt battery would probably be okay. But a 12 volt, that'd be like a regulator on your car that runs a little high, which Oldsmobile had in the 80s and 88 to about 90 for a couple of years. They were charging, the regulators were off for some reason. They escaped through the inspections. And the hoods would get cooked when the battery exploded. And it was due to improper voltage on the regulator. Had a recall on it. My dad owned one, that's how I know. So that's, again, a half wave, and it's not using the center tap, it's using the entire transformer, and it's less than half. So anybody that's going to go DC, they need to be aware of that. Fortunately, we can do a little design work to get around this problem, and we'll talk about that later. Any questions? That's what I'm going to do on halfway, and that's it for halfway. The rest of the time will be on full wave. Does it start to make any sense, Jeff?
Somewhat. I think I got the gist of how to get the formulas, but
That formula up there. Just need to know the RMS is 0.707 times the peak, and the average is 90%. That's all we're dealing with now until the end of the quarter. That's all you need to know in Ohm's law. That's it. All right. Can you see that okay? I don't help. I don't know.
it's better. Sorry.
Is that better?
It's all right.
I mean, I can see it fine both ways.
Either way.
Either way, either
With the
way.
lights on, fine.
Does it make any difference to the
It adjusts.
photographer?
It'll adjust. Should.
Is it easier, Brad, to see that off or on?
It's fine both ways.
It's fine both ways. Okay, cool. All right. This is called the full wave conventional, and I'll tell you what I'm going to do though. That is a nice drawing, and but I think I'm going to redraw it out here. So I'm going to put this in color, and we'll just shut this off for this part. All right. This will be the full wave conventional, and we'll put the transformer in black. And since we're dealing with 120 volts out of the wall, we'll go with that. And we'll draw this dial in red. And we'll put this dial in blue. And then I'm going to connect these two together. And to that, I'm going to put a load. And I'm going to connect the center tap. We'll call that the center tap. It's 1, 2, 3. Well, let me, I still need one, don't I? I need 3 there. Just so it looks like it's in the center. 1, 2, 3. And then here's the center tap. And what I'm going to do is tie the center tap to the bottom of their load resistor. And this will be ground. 0 volts. That's our reference, chassis ground. Okay. Now let's look what happens when the input is positive and then when it goes negative. Now we'll make this, we'll go ahead and make this 2 to 1 again, just like the last time. And let's just trace the path of current when the input is positive. And so I'll do that out here too. There's positive and negative. And this has actually it's going to have a 30 volt average. Or, I'm sorry, RMS. I think. The reason is you'll see right here. Now remember, how does current flow through a diode? Against the arrow, right? So we'll just go ahead and draw a current flowing in this direction. And when the input is positive, here's what you have to know. If you've had 111, you know this, and I guess you all have. Or is that true? Somebody said they didn't have it yet? I want to use blue for the low for this in here. All right, and then come down here. So here's what's going to happen with the center tap. Pay close attention. It happens without the center tap also. When the top side of a transformer is positive, what's happening down here?
Negative.
Negative.
It's negative. And when the top half is negative, this is gonna be positive. Everybody understand that? That's the nature of a transformer. See, in a transformer, since there's no connection, no electrical connection here, everything depends on the magnetic field. And what happens is, you have a north and south pole, and magnetic current flows out of the north into the south, like that. That's the magnetic field, okay? And whenever you ground the center tap, you see what happens. If this is a magnetic field, there's a north and south pole, we know they're opposite polarities. Right? So that's why, no matter what, anytime you have a positive on the top side of a coil, the bottom side will be negative. The only way around that is to ground it like we did on the half wave, and that makes it 0, but you're not going to use center tap there. All right, so here's the path when the input is positive during this time. This is the input here. And here's our out. So what's going to happen is we're going to get this, and then I'm just going to show you why. Here's what happens. Current flows through here, and it comes down and it goes through the center tap. Now why? Here's what happens. There is no path here. Now, why not? Because this part of the transformer is tied to this diode, and that point, at this point right down here, is negative. At that same time, this is maximum positive, this is maximum negative. That means this diode is on and this diode is off. So what happens is, that's an open circuit, so the current is forced, and we're going in this direction, notice. We're flowing negative to positive, and the current's flowing up through that transistor. This is positive, and that's negative. Now, how do I know that's positive for sure? By looking here. That diode, when it's on, is a direct short. And that's all during the positive half. That means that has to be positive. So there's no question that the path of current is only going through one half of the transformer. And it's going from negative down here to positive. And this has to be positive because that's a direct short, and we're only looking at the positive part of the wave. Does that make sense to you? Yay, nay? No?
Yeah.
That's pretty, I think I'm trying to make it as obvious as I can. That's why I'm using color. Now let's look at whenever it goes negative. Now during this time, the diode is off. It's an open circuit. At least this one is, right? So it's like an open circuit. And when this is negative, what happens down here? Positive. So we know current's going to flow in that direction against the arrow, right? When it's on. So here's our path. Watch carefully. Notice I'm going down. Notice that's the same direction. Going up through there. And when I get to here, that's an open circuit. So I go right down here. And there's the path. But notice, the direction of current flow did not change, did it? So what happened, this is still positive, and this is negative, because the diode is acting like a one-way traffic thing. It's saying, it's taking that positive here during the time that's negative, and it's routing the positive up there. You see, it has no choice. It's the only place it can go, and it puts the positive up on top again. And then, so what happens is, when that's negative maximum, this is going to be a maximum positive. When that's maximum negative. That is what you call a full wave conventional power supply using the center tap and only 2 diodes. Questions?
So, if you flip those diodes around,
It's just going to be 2 negative pulses. Yeah.
what? So if you only flip one of them around, it would give you 2 negative pulses.
If you flip one of them around,
Would it-
no. If you flip one of them around, you're gonna have a direct short across the transformer, the secondary. It's
That's
gonna
what it is.
vibrate and hum and smoke
That's what I was gonna say, it wouldn't work if,
and burn.
it wouldn't work if they were two separate directions.
No, see, you just look at this. If I turn this around and get it backwards, and students have done that before, believe it or not, get them hooked up wrong, and you do that, notice, when this is positive here, look what happens. This is a direct short to there, this is turned on and that one's turned on, and you got a direct short across that secondary. Smoke, guaranteed. That's a direct short, 0 ohms, superconductor.
So if you hook that up wrong, it's just gonna burn the shit out of the thing?
Yep. The transformers on our trainers, I've heard them sitting there vibrating. It says, "Oh, whatever you do, shut it off quick. You're burning the transformer." The transformer said, "It's starting to shake," and it shakes. I can feel the vibration. You can hear it. I'm saying, "You got a short, guys. Shut it off quick." And the diodes both smoke because there's nothing to limit current other than that pretty low resistance secondary winding. That's the only thing that's limiting current. You have to force it through the load. If it don't go through that load, it's a direct short, right?
I was gonna ask you, because we did that in the class I had tomorrow night. We hooked up a motor backwards, and that's what happened. It started making a real funny noise and heating up and stuff.
AC motor.
Yeah.
Yeah. All right, question, what's the voltmeter gonna read? We have a 2 to 1, just like the last time. The only thing is, we're only using 1/2 the transformer on each cycle, right? So the true RMS voltage is not 60 anymore, it's 30. So what's the voltmeter gonna read? Notice it's not 0 half the time now, Jeff.
So it'll read 30?
Yes, it will. Actually, it'll read 27 because
Oh,
that's,
yeah, the average of it.
that's the DC voltage now. This is DC, right?
Yeah.
So it's gonna be average, which is 90% of 30, so 3 times 9 is 27. And will we, now notice, that's the same as the last one, wasn't it? 27. So now why would you use two diodes when you could do the same voltage using the whole transformer with one diode? Why would you? Well, as a battery charger, you wouldn't. You wouldn't do that because it's the same output no matter what. But when it comes to power supplies, if this is halfway before it repeats, like that, but this is repeating, this repeats 1, 2, 3, when this only repeats twice, right? Actually repeating itself once. Now notice, what was the definition I gave you for frequency last week? Frequency is what? The number of times a what?
Wave repeats itself in 1 second.
A number of times a wave repeats itself in 1 second. So, what's happening here, in a half wave, it repeats itself from here to there, where this repeats itself from there to there. So this frequency must be, where I only get 1 here, I get 2 there, therefore it's twice the frequency. So we know this is 60 hertz right here, right? So this frequency is 60 hertz. And what's this frequency then? It's twice that. That means you get 2 waves. Now, the only time that's an advantage is if you're going to filter it, the power supply, which we'll talk about a little bit later. Mainly most of next week, but what happens, this is easier to filter. It's like if you were driving a car pretty fast and you hit here and there, and you have to catch those, you'd be at the same level, you wouldn't feel a whole lot of bump, would you? But what if you had to jump from here all the way to there? You'd have to travel twice the distance to get to that other peak. So this is called smoothing the output. We make it a little bit smoother, it's not as rough as that would be. And to a capacitor, that's important. And you'll see later why that is. Questions? That's a full-way conventional, not used a whole lot, because you don't gain anything. Other than, if you're gonna filter, then you'd wanna use the, because the capacitor, you could use, if this required a 1,000 microfarad capacitor here to here, and this distance from that peak to that peak is half, which you can see that it is, from here to there, that's half, it's the same as that. It's 1/2 of that, you see that? If this is X, this is X over 2, it's 1/2 of it. So what that means is, if this requires a 1,000 microfarad capacitor to filter it, this would only require a 500 and get the same amount of filtering. Why is that important? Because the capacitor turns out to be really, other than the transformer, it's the most expensive part you can have in a power supply. Because the capacitor are typically in the 1,000 to 5,000 microfarad, up to 10,000 even. And a 10,000 microfarad will cost you about $8, where a 5,000 would cost you about half that, about $4. So if you were gonna build power supplies, if you were a company and you was gonna be making these things, you would say, I'm gonna add a second diode here that costs about 8 cents, right? Compared to a $4 savings. Well, you can see, why not just spend 8 cents more and cut the capacitor in half, and now you've saved yourself about $3.92 saved, if you'll just put one more diode in there.
So
That's when the CEO earns his money.
So they're one of the cheapest things you can do to the circuit is diodes, putting diodes in the real cheap.
The diodes are like 10-cent items, yeah. So they're cheap. The transformer's not really much more expensive than the capacitor. We're talking about small. You've all seen these adapters. They're everywhere, aren't they? Because all the toys you play with today are electronic type toys, computer, smart little toys, smart machines and all that. They're all running on, well, if they're computer, they're 3.7 volts. Maximum 5 if it's a little older. So, I mean, you don't need much power, really, do you? But what they do is they'll sell you that little box, sometimes more expensive than the toy itself, the little remote control car or whatever. That little adapter, because it's got a transformer in there, and it may or may not have, it doesn't really need more than one diode, but the more expensive ones will either use 2 or 4 diodes. So you can go to Radio Shack and get an adapter for $3, or you can pay $12. Just get a little, you're gonna get a full-weight bridge type of converter, converting the AC to DC. And that's the next one we want to go in, and then we'll take a break. I want to give you the full-weight bridge, and this is the best power supply that you'll find out there in the adapters for AC to DC converting. So let's take a look at the full-weight bridge and see why it's so good. Hey, Ron, would you take that towel there and, well, you can take this right here. Take this right here and wipe that board real clean. I may have a color diagram already done on that, and it'll be nice and clean and neat. And, smartboard? Yeah, the smartboard. Let me see if I've got that diagram in here.
I was looking where it was, but I noticed it was his computer.
I didn't know what it was. At first I thought it was his phone. I was like,
I thought it was a computer in the back corner, it sounded
schematic, but it's not in color, Jeff, I don't know.
But why am I getting aimed at here?
You always do.
I know.
Well, you kinda made fun of my color last week, didn't you?
No, I wasn't.
Oh, you didn't?
I would never do that. I'm a silent guy unless I get bit on.
It's not in color, but I'll kinda try to make it in color, at least it'll be nice and squared off. And, I shut that off, didn't I? It'll come up here pretty quick here. Oh, do that.
Well, yeah, you got
Enter, video, now it's on. There we go. I'm gonna do it like that. Down here just a little bit.
you got a color one in the book?
Do they have a color diagram?
Page 62.
Let me see what it's like. Yeah, that's.